Right, so this is going to be week 4. The idea of pure breeds is that essentially there's no mix, so they're going to be homozygous for both of the alleles. Now I'm going to talk about actually setting up a dihybrid cross. I want to note that if I have homozygous dominant in both cross with homozygous recessive, I get 100% heterozygous. Now, what actually happens when we cross the heterozygous with the heterozygous? A lot of people get confused on how do you actually set up the dihybrid cross. So let's say on this side we want to use this parent. Essentially, we're going to first start off by drawing what things can this parent actually contribute to the child. So they can only contribute their own genes, so it has nothing to do with this parent. Let's just look at here. If you've done calculus, you'll remember this thing called FOIL method. So this cross with this cross with that, this one cross with that one, and that one cross with that one. As such, we can have this, we can have this combination, and that combination. And the same thing here. So it has nothing to do with that parent. We're just looking at this parent. And what alleles can this parent contribute to the child? They can contribute these two, or these two, and then these two. So we end up getting this, and that. If you were to multiply all this out, you're going to get a certain ratio, and this is only when you have heterozygous F1. So this is an F1 right here, because it's the first cross of a homozygous with a homozygous recessive with a homozygous dominant. So these are considered your F1s. And essentially, now that we're crossing our F1s, you're going to get this ratio of 9 to 3 to 3 to 1. The genotypic ratio is what I'm actually drawing out here. That's going to be different. That's going to be 1 to 2 to 1 to 2 to 4 to 2 to 1 to 2 to 1 from memory. I think, yeah, that should be right. This is going to be your phenotypic ratio, so the things that you observe. Remember, you could have, let's say, a big T with a small t. That's still going to be seen as a big T. So try it out, draw out a dihybrid cross, and just get that thing done. Now there's this thing called Mendel's law of independent assortment. I'm not going to write it out because it's very simple. All it's saying is that two different genes will randomly assort, and they will basically do so due to the homologous chromosomes pairs in metaphase 1 of meiosis. So you're having this crossing over. This is allowing for gene variation, and it's allowing for parental gametes and also recombinant gametes, which are just a mix of the two. Closer to each other on a chromosome, there's a higher chance of them being inherited as a single unit. This is essentially what linkage is. So if they're closer on a chromosome, they're more likely to be linked. Now, what does it mean if they're linked? Well, essentially, what you will notice is that the paternal haplotypes are more than the recombinant haplotypes. So essentially, recombination is where genes kind of mix with each other. And what you end up noticing is that for those genes that are linked because they're closer to each other on a chromosome, there's essentially this recognition that when we look at the kids, they seem to be more representative of the parents' original genes rather than a mix of the two. And another answer from Google is just there's also reduced recombination frequency. So during meiosis, if you'll recall, homologous chromosomes can be exchanged and swapped over in a segment called crossing over. And essentially, if two genes are really close to each other, the likelihood of them crossing over is very low. And that kind of makes sense. And as a result, there'll be fewer recombinant offspring and therefore more paternal haplotypes. Now I'm going to talk about epistasis. And if you'll recall, essentially we always have this dominant allele, right? So let's say that in this case, our BB, or uppercase B's, are dominant over our E's, right? And what ends up happening, though, is that when you have this very special lowercase e, or basically our recessive alleles come together in an individual, they actually defy the normal rules of dominance, and they become dominant over B. And I like this example of the Bombay phenotype because this is also an example of epistasis that just makes more sense for me. So you can have all your phenotypical ABO blood types. However, if you have a special phenotype of having an HH, it can actually change the terminal sugar, and you automatically show phenotypical O blood type regardless of your actual allele. So you could have two uppercase B's, two dominant homozygous B alleles for your blood type, and technically you should be B blood. However, because you have this HH and because of epistasis, you're going to show a phenotypical O blood type. Now, what are the different types of mutations? We have our base substitutions, we have our deletions, insertions, and then we have dynamic tandem repeats. So in terms of our base substitutions, it's usually one base for the other, but we'll talk about some different subcategories. So missense has two categories, conservative and non-conservative. Conservatives are where basically you just have a very similar protein, hence you still have good gene function or similar gene function. Non-conservative is, let's say you're making a similar protein but not the same protein. So recall, 3 bases usually lead to the production of one protein. However, that one protein can be made from many different base combinations. So let's say you substitute a base and you get, let's say, the same protein, but you still substituted the base. So that would be a conservative missense base substitution type of mutation. A non-conservative would be like let's say you substitute the base, you got a different protein, but it's still a similar protein, hence non-conservative. And then a nonsense mutation is just where you created a stop codon, so you're essentially preventing gene function, and that's usually your more problematic mutations. Now, deletions are really problematic, and so are insertions of one base, because what you're doing is whatever proteins you had lined up, you're essentially pushing them all over to the right. So if you had GAT, this is now going to be, and you push it over, you're now going to start with an A. So it could be AT and the next one. The point thing is you're essentially going to shift all the bases over, and essentially you're going to change all the proteins down along the line until you hit the stop codon, or you hit some multiple repeated section, or whatever the case may be. So deletion and insertions are usually your worst type of mutations. And then you're going to have your dynamic tandem repeats. All this is that if you have a multiple repeated section, what can end up happening sometimes is likely to incorrect DNA repair or really any other mechanism, but something along those lines. You get multiple repetitions when you're not supposed to have them. So I guess here we went from 4 repeats to 6, and this can essentially change maybe not the actual protein itself, but because it can increase the number of proteins that are made of that protein, you can essentially change the degree of gene expression, which can later on have pathological changes. Super important, you have to memorize this. There isn't really much to memorize. A lot of it is common sense, like if you have a dotted line, that's adoption. A straight line is going to be generation down. Partner is going to be generation sideways. So this is something called a pedigree chart. What a pedigree chart allows you to do is it allows you to basically check what does a disease look like throughout a family. And so if you recognize something as if a disease has only been affecting, let's say, females, this may hint that this disease is mitochondrial inheritance. And what a pedigree can also do is it can give you a really good chance of detecting whether this is something that someone's future kids may have, or whether it's a one-off thing, or this is an X-linked disease, or has this been something that's been passed down by families? Because let's say couples are having a kid, so they may want to predict the chance of having certain diseases in the family, and then it kind of serves as a type of genetic counseling, as it allows you to be kind of ready for what is to come. And then obviously we have some technologies that can be used to, let's say, reduce the chance of having those diseases. Maybe search on Google what a pedigree chart looks like. You're going to have questions in the GLS which are really good, and honestly they're all you need as to drawing out different pedigree charts. There's this one video on sex-linked inheritance. It does a way better job than I can do, and it's 2 minutes long, so I'm not going to recreate content when content already exists. And then there's also this video, which is 5 minutes, and it explains kind of a more examinable X-linked inheritance and crossing over tables and how to make that. So that's 2 minutes, 5 minutes. Luca's notes, again, I'm not going to recreate something if something's already perfect. So I just pulled this off Luca's notes, which is what are the features of X-linked recessive inheritance. Here are a couple that you can recognize. Honestly, this is going to make more sense once you watch these two videos and do the GLS. You have a half chance of brothers of affected boys being affected with X-linked recessive, I believe. And then in terms of X-linked dominance, you're going to see fathers to daughters only. This is because males have that Y chromosome there. Hence, if something is X-linked, it's only going to be on the X chromosome. We know that fathers pass on their X chromosome to their daughters versus them passing on their Y chromosome to their sons. Hence, if it is X-linked dominant, you only need one X-linked chromosome to have it. Therefore, fathers will always pass it on to their daughters, and there usually is a female to male prevalence of 2 to 1. Now, in terms of mitochondrial inheritance, I already talked about this. Only females can pass the disease. Technically, you could only really see this through a pedigree or if it's verbally said.